As time has progressed, vehicles have undergone the addition of emission-reducing components and systems. Of all these different systems and components, none is as significant as the catalytic converter. The catalytic converter was designed and implemented on vehicles for one reason: to reduce exhaust emissions. All catalytic converters need heat to function efficiently, requiring an operating temperature above 600 degrees Fahrenheit. When HC and CO are oxidized inside the converter, heat is produced. And the more oxidizing a converter does, the more heat it gives off. Because of this, an efficiently functioning converter will have an outlet temperature that's hotter than the inlet temperature. How much hotter depends on how much converting is taking place inside the converter. There are several different styles of catalytic converters used on today's vehicles. But these styles are merely different combinations of two different types. The first type is the oxidation catalyst, which is sometimes called a two-way catalyst. The oxidation catalyst reduces HC and CO emissions by oxidizing or converting them to CO2 and water. For an oxidation catalyst to work effectively, it requires oxygen. But in automotive engines, exhaust oxygen levels are constantly changing, and often in low concentration levels. To keep the level of oxygen more constant, a secondary air system is sometimes used. On this style of oxidation converter, outside air is added into the exhaust stream in front of the catalyst. This ensures the catalyst will have an adequate supply of oxygen to perform the oxidation process. The other type of catalyst is the reduction catalyst, and its primary purpose is to reduce NOx emissions. As an added benefit, as NOx is being reduced, so is CO. In fact, for a reduction catalyst to reduce NOx emissions efficiently, CO must be present along with low levels of oxygen. This is the opposite of an oxidation catalyst, which only functions efficiently when oxygen levels are high. In the reduction catalyst, CO and NOx are converted to CO2 and harmless nitrogen. The air-fuel ratio can significantly affect the efficiency of a reduction catalyst. A lean air-fuel mixture results in high oxygen and low CO levels in the exhaust stream. When this happens, the catalyst can't reduce NOx effectively. The dual-bed three-way converter houses both an oxidation catalyst and a reduction catalyst. Consequently, it reduces HC, CO, and NOx emissions. The catalyst in the front of the converter is the reduction catalyst, while the oxidation catalyst is in the rear. A secondary air injector port is positioned in the middle of the converter to keep the injected air from flowing through the reduction catalyst, as this would decrease its performance. And this is also why the reduction catalyst is placed at the front of the converter. The oxidation catalyst is placed in the rear of the converter, so the oxygen-rich injected air can flow through it, increasing its efficiency. The single-bed three-way catalyst also reduces HC, CO, and NOx levels, but instead of using two different types of catalysts, it uses only one. And with this type of converter, no secondary air needs to be added. Considering that the oxidation process likes oxygen and the reduction process doesn't, you're probably wondering how they can work together. Well, a closed-loop emission system makes this work because it adds and subtracts fuel based on input from the oxygen sensor. This causes the air-fuel ratio to vary from slightly above stoichiometric to slightly below. With a slightly rich mixture, the CO exhaust level is high and the O2 level is low. When the mixture goes slightly lean, CO levels drop and O2 levels rise. This cycling between rich and lean CO and O2 levels, when the engine is in closed loop, allows the single-bed three-way converter to effectively perform both oxidation and reduction processes. On systems equipped with a single-bed three-way converter, the air-fuel ratio control is critical to the converter's efficiency. it's important to understand that an overly rich condition will reduce the oxidation efficiency, but it won't drastically lower reduction efficiency. On the other hand, an excessively lean condition will lower the reduction efficiency, but not drastically lower oxidation efficiency. Properly functioning closed-loop fuel controls ensure that both oxidation and reduction processes operate efficiently. If you're involved with repairing emission failure vehicles, your ability to accurately diagnose a good catalytic converter from a bad one will be vital to your success. Although there are a number of different catalytic converter tests, the most accurate is the pre- and post-catalyst emission reduction test. This method works on the principle that if the converter is reducing emissions, the emissions leaving the converter will be lower than the emissions that entered it. To perform this test procedure, a small hole is drilled into the exhaust system before the catalytic converter. With the engine and catalyst at normal operating temperature, the emission analyzer probe is inserted both before the converter and at the tailpipe. Then these measurements are compared. If the converter is working, the tailpipe readings will be lower than the readings taken before the converter. How much lower depends on the efficiency of the converter. But remember, when performing this procedure, any secondary air that's added to the exhaust, such as that from an air pump, needs to be eliminated. Otherwise, your emission readings will be wrong, indicating a reaction took place when it may not have. To determine the overall condition of an oxidizing catalytic converter, you can perform a temperature differential test. This test operates on the principle that a working converter will increase in temperature. To ensure the accuracy of this test, run the engine until it reaches normal operating temperature. Then, create a misfire by disconnecting and grounding the spark plug wire. This increases the work the converter has to do by adding high levels of HC and O2 to the exhaust. With the engine running with the misfire, measure the converter inlet and outlet temperatures with a temperature probe. A functioning converter should have an outlet temperature that's at least 100 degrees Fahrenheit hotter than the inlet. When performing this test, do the temperature checks quickly because the converter will overheat after a couple of minutes if it's working properly. The disadvantage of this test is that the reduction efficiency for HC, CO, and NOx cannot be determined individually. A catalytic converter is designed to reduce the normal emission levels from a good running engine to even lower levels. However, they're not designed to lower excessive emissions, which are usually the result of some fuel system, ignition system, or mechanical problem. A catalytic converter that's constantly being overworked from excessive emissions will eventually lose its efficiency and require premature replacement. Even though a new catalytic converter may temporarily lower these excessive emissions, it shouldn't be considered until the actual cause of the problem is identified and corrected.